we're going to get started with our next session on machine learning for accelerated science and engineering. Here we're going to be hearing short talks from three speakers, Yunwei Zhang from Cambridge University, Julian Kates-Harbeck from Harvard University, and Felipe Oviedo from MIT. And they'll be talking about different ways in which machine learning is used to accelerate the process of scientific and engineering discovery across different applications, including batteries, solar panels, and nuclear fusion. So if all three of the panelists are ready to start, we'll start with Yunwei. Yunwei, are you able to share your slides?
Sure. Can I do that now?
Yes, go for it.
Oh, okay. Okay. Should I mute my video? Okay. Hello, everyone. I'm Yunwei. I'm happy to be here to share one of my recent work on the application of machine learning in identifying battery degradation from impedance spectroscopy. Here is the outline of my talk. The first, I'm going to briefly introduce.
Sorry, Yunwei, we're not actually seeing your slides at the moment.
Oh, really?
Nope, we're seeing your face.
Oh, okay. Oh, let me.
The green button on the lower panel.
Oh, sorry.
You're fine. You're fine. Take your time. Take your time.
Got it.
Cool. So we're seeing. Yep, we're seeing them in full screen. Perfect. Perfect.
Okay. So here's the title of my work: the identifying battery degradation from impedance spectroscopy using machine learning. Here is the outline of my talk. Firstly, I'm going to briefly introduce the background of the lithium-ion battery degradation study, and then I'm going to mainly introduce how I combine machine learning with the impedance spectroscopy to predict the battery degradation and make the battery diagnosis. And finally, you will see we develop a very accurate, quick, and friendly method for battery prognosis. Here, let me briefly introduce the lithium-ion battery. The batteries, like people, degrade over time, and in the cartoon in the middle of this page, it shows that the lithium-ion battery degradation is very complex. Here, I only show you several battery degradation mechanisms. For example, the growth of the ICI layer, shown as the green part, and the surface cracking for the anode materials, and the loss of the active materials. But no matter what the battery degradation mechanisms are, they will eventually lead to the capacity fade, shown as this plot. And before I go through into detail, let me briefly introduce several basic concepts for the battery research, and you will show the definition of these things in my following talk. The first thing is the end of life. Usually, the capacity of the battery fade to 70 to 80% of its original capacity. We are going to say that the battery is going to reach its end of life. And this, how do we identify the state of the health? The capacity is a key indicator. The equation is equals to the normal capacity at the current stage divided by its original capacity. And another thing we concern a lot is that the remaining useful life of the battery is the remaining number of discharging cycles before it reaches its end of life. And nowadays, people pay more and more attention to the battery issues. According to this survey from FDA, you can see up to 50% of the survey calls in hospitals relate to the battery issues. And according to this association, they report that the battery management emerges as a top 10 medical device challenge. That means the battery prognosis is become more and more important. On the one hand, it can notice the user when should we replace our cells to avoid any dangerous capacity fade. And on the other hand, it can notice us whether we should recycle the battery as a scrap metal, or we can still use them for second life applications, which can help us save a lot of energies and materials. So, but however, let me emphasize here again, you can see the capacity fade is a totally non-linear process, and the different batteries, they degrade in such a different way that makes the forecasting of state of health and the remaining useful life is a really challenging problem. The big data, we know that the big data enables the data-driven method. I'm going to show you one case here. It's an application of the machine learning in battery prognosis. For example, here is a machine learning model based on the historic capacity fade, the capacity data, and it's going to extrapolate the capacity curve to predict the state of health. And you can see in the short term is quite good, quite accurate, and with a very low uncertainty shown as the shaded area. However, for a long-term prediction, you can see the uncertainty is very large. And another thing is that the capacity, accessing capacity is very expensive and time consuming because you need to fully charge and fully discharge the battery to get the capacity. And on the other hand, it can cause damage to the cell when you fully charge or discharging it. So the questions came up here is that, can we find a better way to do the battery diagnosis? The first thing came to our mind is the electron chemical impedance spectroscopy. It's a very powerful technique to probe the impedance characteristics of a battery. Here, I'm going to show you how this technique works. It will generate a small amplitude AC voltage here as the diagnostic signal and pass the signal to the battery. And then we collect the response of this signal, and then it can help us to analyze some electron chemical reaction happened in the cells. And you can see the voltage we used here, or the simulated signal we generate here is very small, so it won't do any damage to the battery. The response of the signal is a typical is the EIS spectrum. It's a typical Nyquist plot, and the y-axis is the real impedance, the real part of the spectrum, and the y-axis is the imaginary impedance part of the spectrum. And this spectrum is a function of frequency. The advantage of EIS is very quick. You can test the EIS at any state of the charging state or discharging state, and it's non-invasive because the signal you used here is very small, and it's very informative because it can show you something correlate to the impedance or the resistance. For example, here this part is corresponds to the intrinsic resistance, and the spectrum here it represent the intrinsic resistance and something correlate to the charge transfer resistance. And here is the EIS spectrum we collected during cycling, and you can see the EIS it changed with the cycle number. So definitely is a good indicator for degradation. However, how should we read it? The basic idea here is that can we use machine learning to capture the subtle but persistent change of the EIS, then to predict some degradation of the battery? So here the idea is that, so the first, what we have done here, firstly, we have to generate the EIS database by ourselves. So we cycled 12 corn cells in total at 3 different temperatures, 25, 35, and 45. Here's the corn cell, commercial corn cell we use. You can buy them from Amazon. And eventually we collect over 20,000 EIS spectrum. And the input of the model is we want to fit the entire spectrum to the model. So it's going to be a multi-dimensional, and we just feed the entire spectrum without doing any hand picking. So it won't introduce some bias or errors to the data set itself. Here is the expression of the input. And the goal of our method is to estimate capacity and predict the remaining useful life of a new cell using a single EIS spectrum. So the output of the model is either capacity or remaining useful life, the remaining cycle number. So a broader idea is that we want to build up a EIS dictionary, then we could able to identify the health of a new cell by measuring its EIS and cross-referencing the dictionary. Here I show you the detail of the model. I'm going to use a classic Gaussian process regression, but with an automatic relevance determination kernel. The advantage of using this kernel is that we remember that my input is multi-dimensional. Actually, it's including 120 dimensional. So the ARD kernel, it assigns a sigma term to each dimension and some frequency. And in our case, each dimension represents a certain frequency. So this method, this kernel going to show us that some frequency are more important than others in terms of determining whether two spectrum matches. So here I'm going to show you the results of our model. The first model we built is the EIS capacity machine learning model that used the model to estimate the capacity. And by estimating capacity, then we can identify the state of health. And for the first case is the prediction results under 25 degrees. The blue curve is the measured capacity, the real capacity, and the red curve is the predicted capacity. And you can see it's quite accurate. And the uncertainty shown as the shaded area is also okay. And here's the case for 35 and 45 degrees. Maybe you comment that the accuracy of these two cases are sort of lower than this one. That because we lack of training set for these two temperature compared to the 25 case. And here I show you the second model we built is the EIS remaining useful life machine learning model. And by using this model, we can directly predict the remaining useful life of a testing cell. And you can see these three cells cycled under three different temperatures. They have the different end of life. Around 150 and 250 and so on and so forth. And here for the first one, you can see our model can accurately predict the remaining useful life of a battery, of a new battery, which haven't seen by the training set before. And in the end, I'm going to show you that our model can not only give you an accurate prediction of the state of health or remaining useful life, but also the machine learning model can help you to interpret the EIS spectrum. So that's the results of the ARD method. For each temperature, the ARD method only shows 1 to 2 salient frequencies that correlate the most to the battery degradation. For this one, the 25 case, it assigned the frequency at a lower frequency region, less than 20 hertz. And considering the region of the frequency is 0 to 20 million hertz. So the 20 hertz is quite lower. And I highlighted the salient frequency in the raw data, shown as the blue and green curves. And remember that the frequency at this region, it corresponds to the charge transfer resistance of the system. So the conclusion we got here is that the machine learning can capture the subtle but persistent correlation at the salient frequency. And you can see here is a linear, close to linear relationship, but it's very hard, it's impossible to tell by our naked eye. But the machine learning model can clearly show that trend. And the second thing we find is that the machine learning can help us to find out that it's the change in the interfacial property, that is the charge transfer resistance that underpins the degradation. I share my code online, so if you are interested in, you can check it and download it. So here I'm going to make a conclusion of my work. The first thing, we show that the Gaussian process can identify degradation patterns of lithium-ion battery from EIS. And the second thing is that our model can accurately predict the state of health and the remaining useful life of a new cell at any point of its life from a single EIS measurement without knowing the cycling temperatures. And the model has shown great potential to be used in an online battery management system. And the model can also shed light on the degradation mechanism by providing the salient frequency located in lower frequency region. So in future, I'm going to test my method in other different battery system with higher capacity, such as the car battery. Before I close my talk, I want to thank my supervisor, Alpha Lee in Cambridge, and my experimental collaborators in Newcastle, Uli Steeming and Qiao Chu Tang. So the whole project was funded by the Faraday Institution. Thank you all, and open for questions.
Thank you so much, Yunwei. What we're going to do during the session is we'll kind of take all the talks in a row and then take the questions at the end. But
okay.
sort of while we're transitioning to the next speaker, who is Julian Kates-Harbeck. So Julian, feel free to share your slides. We did get one question in the audience, which we can go for it now, which is, Yunwei, what are the factors considered in uncertainty quantification?
Sorry, which one? What other factors to consider in the uncertainty quantification? I don't quite understand the first question. Let me go for the second one. Does the user need to build a new? We need to build a new EIS library for every different kinds of battery, because the degradation mechanism are different from each different battery system.
Perfect. Thanks, Yunwei. And Vijayant, if you could just clarify your question in the chat, we'll get to it at the end of the session.
Okay.
Thanks, Yunwei. So with that, let's turn it over to Julian. Julian, go for it whenever you're ready.
Sounds good. I hope everyone can hear me, can see the slides all right. Thanks, Priya, for giving me the chance to speak here. This is clearly a very awesome collection of topics here on this panel. So thanks to you and the rest of the organizing committee. I'm going to talk a little bit about applications of machine learning, deep learning in particular, to nuclear fusion. So just a very quick background. The idea of the idea of fusion power is to harness the same reaction that takes place in the center of our sun here on Earth. It's sort of a almost too good to be true technology if we could really make it happen. Currently, we do not have viable nuclear fusion reactors, but if we could make it happen, it would essentially provide limitless, sustainable, clean energy in a centralized way that could be scaled across the whole world. And it would honestly be able to solve a lot of our energy problems with high probability. The issue is that it's a pretty tough scientific and engineering challenge to get there. And today I'm going to basically talk about how deep learning has helped us at least address one of the core challenges, one of the core hurdles on the way to making fusion power a reality. So the way that fusion works is it's based on, or one of the technologies that is promising to make fusion a reality is the Tokamak. So the Tokamak is a toroidal device, and it uses magnetic fields to confine a hot hydrogen plasma. The plasma is heated to such a degree that the nuclei in the plasma start bumping into each other and fusing together, the same that happens in the center of the sun. And this is a very promising and sort of elegant geometry that allows this to happen. It uses very powerful magnetic fields and a very hot plasma, and the combination thereof has a lot of free energy. There's a lot of free energy in the system and can sometimes lead to instabilities, especially magnetohydrodynamic instabilities, where the plasma interacts with the magnetic field in a self-consistent way. And these instabilities are an issue. And I'll get into exactly how that's an issue in just a second. But here's a little picture of what one of these tokamaks actually looks like from the inside. This is the Joint European Torus, actually the largest currently operating tokamak in the world. It's in the UK. And sort of photoshopped in there, you can see on the left what it actually looks like when a plasma is running. The lit up parts there are touching the diverter at the bottom. That's actually on purpose, and that's the coldest part of the plasma. So the plasma is radiating at such high frequencies, or it's so hot that the coldest part of the plasma is the part that you can see. That's sort of this purple glow. And it's sort of only very moderately touching the walls, and that's what a good plasma looks like. Usually we have this plasma running and we can monitor it with various diagnostics. So a lot of these holes there in the wall are diagnostics that measure various properties of the plasma. But as I said, there's lots of free energy which can lead to instabilities in the system. And these instabilities can cause the plasma confinement to fail. The way it fails is that the magnetic field changes in such a way that the plasma can actually touch the wall in areas where it's not supposed to touch it. And that then looks something like this. So you have the plasma touching the wall over a wide area. And this has several very bad consequences. Number one is that all the heat in the plasma immediately gets transferred to the walls. And because there's an enormous amount of heat in the plasma, this can cause severe damage to the walls, including melting or even evaporating of wall tiles. Another thing is that a cold plasma has much higher resistivity. This means that the very powerful toroidal current that's usually used inside the plasma, induced in the plasma to help build the magnetic field that confines it, this current is quenched or basically stopped in its tracks. And a very rapid change in current, as you may know from fundamental physics, changes the electromagnetic fields or induces very powerful electromagnetic fields around it. These electromagnetic fields can be so strong that they literally warp the whole structure of the tokamak. So you have this thermal quench, which adds a lot of heat energy where you don't want it, and then you have the current quench, which can produce warping of the structures, both of which are very bad. And these instabilities that I'm talking about here are called disruptions. So the name of the game I'm trying to set the stage here for why disruptions are bad, and now going into what we can do to avoid them. If we had a way to predict when such a disruption would happen, we could do something about it. So one tool here is indicated kind of cartoonish at the upper right is to inject gas. So some of these little openings, you can literally inject neutral gas into the chamber, which then radiates away the heat of the plasma in a more uniform and more benign way before the full disruption hits. So if you could predict when a disruption was going to happen, you can avoid most of its negative side effects. So the name of the game is to predict these disruptions. And I'm not sure the sound will come across on Zoom, but here's a little video of an actual tokamak disrupting. So I'll just play it and hope that you guys hear the sound, but even without, it should be interesting. All right, so you could see how the plasma was sort of benign there in the beginning, touching the diverter at the bottom, and then boom, something happened and the plasma suddenly shut off. So these disruptions, by the way, anecdotally, I've heard that these disruptions can make the entire tokamak, which is sometimes tens to hundreds of tons of steel, jump up by an inch or so into the air when they happen. So this is real stuff, and it's bad. One thing that makes it even worse is that these disruptions get worse with the size of the machine. So here, roughly to scale, you can see a little person to the lower left of both of these devices are two existing tokamaks. JET, as I said, is the biggest that currently exists, but we're building a much bigger one called ITER. And ITER is sort of a really expensive, I think it's one of the most expensive scientific experiments ever built. It's tens of billions of dollars, budget constantly rising, but it's also the first tokamak that is planned to achieve break-even and go way beyond break-even, i.e. produce about 10 times more power than it consumes. So it's a really important milestone on the path towards making a fusion a reality, but it's so large, and the square cube law means that the energy stored in the disruptions is way higher, but the surface area to take that energy in the case of disruption is lower, which means that ITER is actually in a position where it cannot withstand more than a handful of disruptions at full power. So JET and D3D, you can run thousands of disruptions, especially on D3D, there at the bottom left, to kind of study them and maybe train your models on them. but we need to be able to predict disruptions on ITER without a big training set. And this is going to be a really important part of the story. So remember that fact. We can't train on ITER. Okay, so what do we do about disruptions? People have tried first principles simulations of the plasma, which are extremely advanced, and it's a whole field of science, and there's a lot of great stuff going on. But the honest assessment here is that these simulations are not yet at a point where they can provide real-time prediction of what's going to happen next. Or what you would really need is faster than real time. There's a few things missing. You don't have enough diagnostic information to really seed this in the simulation properly. And even if you could, they're very far, like we're not even close to being able to run these in real time. And then a third thing is that the physics approximations people make in these simulations typically aren't valid in the highly nonlinear regime close to a disruption. So this is very far away. So people have turned to machine learning approaches. We're not the first to have this idea, but people have traditionally used classical machine learning approaches, which, as people in this audience I'm sure know, have a lot of problems with the kind of high dimensional data that you might imagine comes from a tokamak, which are these very fast time series, and some parts of the time series are not just scalars, they're higher dimensional objects. So I'll get into more details on that in a second, but these classical machine learning approaches are basically our best option right now, but they have their limitations. The type of data that we get from a tokamak is very diverse, and I won't go into that much detail, but basically you can measure all kinds of things. You can measure the density, the temperature, the internal inductance. You can measure the current through various induced coils. These are all sort of scalars that you might, or 0D data. There's also profile data. And this I want to spend a little time on because it's a kind of a subtle point, an important point here, where you take measurements at various radii in the torus. So if you look at the bottom here, I think you can't see my cursor, but if you look at the bottom, the radius is sort of defined from the center of the torus to the edge. And because of the geometry of the magnetic fields, there's very little particle diffusion from the center to the edge, or at least it's much slower than in the poloidal or the toroidal direction. So of all the three dimensions, the radial dimension is the one that has the most meaning, or where a slice through the device would be the most stable. So people like to measure all kinds of quantities as profiles: temperature, gradients, pressures, densities, all kinds of stuff. And these profiles are then one-dimensional objects as a function of time. And we actually have a path towards even higher dimensional data, including 2D data obtained with a technique called ECE imaging. And this is one of the next steps in our research agenda here, but that's not currently included in this talk. So we turn to extend sort of, or stand on the shoulders of giants and extend the existing approaches with some more modern deep learning methodologies. So here's sort of a cartoon of our general approach. So you have your tokamak at the top, and you're getting signals through the various diagnostic channels. These are time series of various scalar signals, so don't worry too much about the details here. Just treat this as a cartoon. You have these scalars as a function of time, and the time step that we use is milliseconds. One note about that is that there's some quantities that change on the scale of microseconds and others on the scale of really hundreds of milliseconds, and this is sort of an intermediate compromise. But we are aware that there's lots of methods that are emerging that can deal with varying timescales, and we're actively looking into those. So in addition to these scalar signals, we have profiles. So the way to look at this part of the chart is that you basically have something. So the top one of these two profiles is the temperature. So the plasma at first is very cold, and then it turns warmer over time, and then at the very end it gets really hot in the center. That's sort of how to read this. So you do a temporal slice through all of this, and then you feed each temporal slice to the deep learning model, which I've just sort of cartoonishly here labeled as RNN, but there's more going on. I'll get into the detailed architecture in a second. And the output is some measure of disruptivity. So it's trained on past disruptions such that the output value rises when you get closer to a real disruption. And then you have to set an alarm threshold. A higher threshold will reduce in less false positives, but also less true positives, and a lower threshold in the reverse. We can really measure performance by tracing a threshold and tracing out an ROC curve. But in a real application, you have to pick some threshold. So you make some trade-off, you pick it. And then when your RNN output ever reaches that threshold, then you can sound an alarm. Hopefully this is far enough before disruption to actually do something about it. In real life, you would need about 30 milliseconds of warning time. So 30 milliseconds is sort of this magic number. That's, if you look at the bottom, there's sort of a thin red line at the end of the time series. That's the 30 millisecond warning time. So this was a real disruption, and we had way more time. So this is great. And then you inject this neutral gas, and hopefully you can avoid all the negative side effects of disruption. Of course, you don't want to do this during every shot, because you ruin the shot. You need to clean things up. One shot, I should say, is a sort of an experimental run on Tokamak. You don't want to do this all the time, so there's definitely a trade-off between false positives and true positives, but missing a real disruption can be a lot worse, especially on big machines. And this is what the architecture looks like. So you have the 1D profiles coming in and the 0D signals. We run the profiles through convolutional and downsampling operations to extract features from them, concatenate those features with the 0D or the scalar signals, and then that full feature vector is fed into an LSTM, which performs the sort of the temporal accumulation of information and of history. Now, we're in this work that I'm presenting, we used an LSTM, but we're aware that there's other powerful methods to sort of gather the temporal information as well, and we're actively looking into temporal convolutions as well as attention / transformer-based architectures right now. So our approach is we're agnostic as to the architecture. We just do what works best, and these kind of choices are just considered sort of a higher level hyperparameter in our workflow. Here's sort of a zoomed in version of this. Okay, here's some examples of some real shots. So in this shot, we had thermal quench around second 5,000, where the temperature rapidly dropped, and this caused actually a false alarm. This wasn't a real disruption. What happened is you had a thermal quench, but you didn't have a current quench. So somehow the plasma recovered, which happens sometimes. What I'm illustrating here is that the RNN really picked up on something that a human might also pick up on. It's pretty reasonable. You have this sort of first stage of the disruption, and then the second stage didn't happen, surprisingly. But even the false positives are sort of useful in this sense for tagging the data and at least interpretable, which we didn't necessarily find to be the case with the classical methods that we tested this against. Here's another example that's interesting, where if you look at the second panel from the top, the radiated power rose over time and eventually led to a disruption, but it's sort of this slow, noisy rise, which is very difficult for classical methods to pick up on because they don't have the ability to see this high dimensional data as meaningfully, whereas our RNN method correctly predicted a disruption over many hundreds of milliseconds in advance. The method does very well on sort of a single machine, but what I really want to point out here before finishing up is this cross-machine prediction. So the idea is that you want to predict on a machine that was unseen during training. So we actually tested this. So we used our two machines that we have data from, D3D and JET, and we trained on the smaller machine and then tested on the bigger machine. And while ITER, this sort of machine that we're now building, won't withstand hundreds of disruptions, it may withstand a handful, especially at low current. So what we did is add a few shots from JET to the training set, just to see what would happen, if that would actually make a difference. And the first thing we saw is, if without adding any glimpse of the testing set, or at least of the same machine as the testing set, the deep learning method really performs much better than the classical method. I mean, the classical methods, this is our area under the ROC curve, where 0.5 is basically a random guess, and 1 is perfect. There's some significant learning going on, but 0.83 is not great. But once we added just a few disruptions, we got to a level that's competitive with what you would get if you trained on the whole JET data set. So this is very encouraging because all methods benefit, but particularly the deep learning method, and particularly the one with 1D profile information benefited the most. And this is sort of, I think, the key slide of the whole presentation. So the idea is only a few shots from the big device make a big difference. 1D profiles, which classical methods haven't been able to use, make a big difference. And cross-machine prediction is really possible for the first time. That's sort of the big story here. I also want to mention that having access to supercomputers allowed us to do data parallel training and automatic parallel hyperparameter tuning, which is key to get to a solution in a reasonable amount of time. And we were able to run on some of the biggest supercomputers in the world, which is very awesome opportunity. And lastly, this also opens up a really interesting path towards moving from prediction to control. So it is much more elegant to sort of actively steer the tokamak in a direction that doesn't disrupt, rather than see a disruption coming and sort of shut it all down in this very unelegant way of injecting gas. So, you know, your environment would be a tokamak. Your control algorithm is based on representations learned by some deep learning model based on similar models that we have trained. Your actions are real-time control, like injected power and coils through various currents. You can measure your diagnostic signals, and your reward is not disrupting, but also other things. You can extend your reward function to optimize for things like fusion power output. So just to summarize, deep learning allows us to use high-dimensional data for the first time, learn cross-machine and generalizable features. It allowed us to take advantage of world-class high-performance computing to do this all in a reasonable amount of time. And it opens up a path forward to go to more elegant active control of the device, which is sort of the holy grail going forward that a lot of people are interested in. Thank you.
Awesome, Julian. Thanks for that really interesting talk. We're going to kind of defer the questions to the end of the block, though there are some specifically for you in the chat. Feel free to respond to those as well. But as we transition over to our next presenter, Felipe Oviedo, and Felipe, feel free to share your slides. But as we set that up, there was one question about what hardware do you deploy on Julian, and how does it interface with the data feeds, generally speaking?
Okay, so I have to say that currently, so the results that I just presented are not actually run yet in real time on the device. And it turns out that this translation of these sort of models that we can train with our high-level Python libraries, translation of that to actually run in real time on a tokamak is quite tricky, because tokamaks can only work with sort of real-time C code. So we need to first translate this model into a real-time C compatible code. And that then needs to run on the often quite not the newest hardware that runs in real time with these tokamaks. So while training and inference for sort of these evaluation purposes offline is run on sort of GPUs like you would do for any old machine deep learning model that you might run, the inference in real time is run on sort of like real time servers that sit right next to the real tokamak. So it's not run on GPUs, and we have to make sure that inference can run on this hardware fast enough.
That's really interesting. Yeah, that's very cool. All right, so Felipe, if you're ready to go, we're ready for you. Thanks, Julian.
You're muted, Felipe, I think. Felipe, I think you're muted.
You should be unmuted now. Yeah, now we can hear you.
Okay, great. Thank you. Sorry about that. So my name is Felipe Oviedo. I'm going to present about machine learning for development of next generation photovoltaics. This is the work with MIT CCEL, the Singapore and MIT Alliance for Research and Technology, and the MIT PV Lab. All right. So why do we need next generation photovoltaics? If we see the IPCC climate change targets, the state that by 2030, we want to aim for like 2 degrees of warming. The only way to get there with the current PV technologies is to actually use deploy up to 8 terawatts of PV in the next 10 years, roughly. The current technology is actually growing very quickly, but it's not able to reach that amount of installations by then. Even if we have things like different financing models, increased debts, essentially, we are also limited. So advanced technologies are cheaper or actually have higher efficiency are actually necessary. And the more we take on this issue, the less impact we will have, of course, on climate change. The targets for this scalable novel PV are high percentage conversion efficiency, high manufacturing yield, so they have to be made with a reproducible process. They need low cost and low degradation rate, so they have to maintain their efficiency in the environment for a long time. One promising technology is perovskite solar cells, which has some of the qualities that we'll like in a new scalable PV material, which is potentially very low cost, high energy conversion efficiency. Manufacturing yield arguably could be fixed, but it's not very reproducible at the moment. And the main issue is that it's not very stable, so it actually degrades and interacts with like humidity or even heat. So the premise here is that machine learning can accelerate this PV development process. And taking from the previous presentations, it could also benefit from a combination of high throughput experimentation. So making a lot of experiments that actually give you a significant amount of data quickly, and physical principles or first principle simulation. Move to the next. So PV optimization is complex and time consuming. It has taken decades from silicon to become market competitive technology. So how can we accelerate this process? And this has to happen at different levels. One is the PV material level, but also in the systems level. When we aggregate materials in a stack to have a full solar cell, for example, gold or glass, etc., they have to be optimized as well. So I'm gonna talk about two projects applying machine learning to optimize these two levels. The first one is gonna be materials. So we wanna optimize the composition of perovskites that have a formula that looks roughly like this, which Ma and Fa are some organic compounds. And then we wanna optimize the combination of these three elements to maximize the stability of the solar cell. How we do it in the lab is actually we are able to synthesize hundreds of these films and then we put it in an accelerated degradation chamber, subjected to constant humidity and temperature conditions, and then we just see the change on using a RGB camera to see the change in color of the film. So the films that are dark are actually good, and as they degrade, they start to become yellow. So it's a quick and dirty way to optimize solar cell compositions in this scenario. So for this, a good approach is using Bayesian optimization. As we know, is in Bayesian optimization, what we try to do is optimize a black box function, and we construct a surrogate model like a Gaussian process model that gives you an idea of the mean and uncertainty in different parts of the space, and then we like sequentially update it to be able to have a better idea where the maximum is. And in order to know where to sample in sequential rounds, what we do is we construct this acquisition function that samples promising areas of the variable space. We can extend this idea to our approach in which we choose compositions. We can synthesize the films, and then we quantify stability with that chamber I show you. So we have this property that makes it very easy to get data in which black films turn into yellow subproducts and they change according to time. So we want to minimize this total change in color, but that's only part of the story. Also, like some of these materials are stable, intrinsically unstable, which means that you could like synthesize them, but they could not like they could decompose even before you start degrading them, or they could be paths that actually are not contemplated by this black to yellow approach. So one way we could do is actually at first principle calculations, which is density functional theory calculations. Of these quantity is called Gibbs free energy of mixing. It's just a quantity of how that measures how stable is the film. It's the material. And so we could like embed this into the optimization loop. For this, we follow an approach of stochastic constraint. Like we have we want to optimize our total change in color subjected to a probabilistic constraint, and then we can build a probabilistic model based on the computed or the simulated Gibbs free energy of mixing. that we could like interpolate with an auxiliary Gaussian process model in this space. And we could also have, since the experiments and theory actually have different biases, different uncertainty, the question becomes, how do you even define a hard constraint here when you are not sure that your fundamental first principle calculations are that exact, right? So one way to do it is with this calibration parameter beta that allow us to, based on like some uncertainty that we know from the calculations, we can like apply it to the constraint. So the way to, once we have the constraint, the way to embed it into the optimization is to multiply it by the acquisition function. And what I will do, as we see here, is it will take the acquisition and cut out the regions that are actually not promising beyond what we are able to measure based on first principle calculations. And then we sample according to where is it pointing us. So we perform this optimization experimentally, and we synthesize around 200 films, which is an exploration of 1% of the potential combinations of chemicals here. And we came out with a 3 times more stable composition in these 4 rounds of learning. It's actually a pretty good result, very promising for like experimental sciences. So now I'm gonna move to the next project, which is Eevee Devices. So what happens when we have this aggregated system? How do we optimize it? How can machine learning be useful in this context? One traditional application of this is choosing the right process variables to fabricate high efficiency solar cells. And high efficiency is essentially a product of current and voltage at a certain point in the curve, which is what we call like how much power we can get from a cell. So usually what we could do is expert guided optimization. So some expert would look at the results, we choose what to change next and what exactly in this complex stack to change. We use Bayesian optimization in some sort of black box optimization loop. So what we proposed was to add this layer in here, which is the material properties or device properties layer, in which we can infer some of relevant physical parameters from the solar cell that actually are more descriptive than these simple output measurements. For example, one is like a bulk lifetime or source recombination in the solar cell. So it's like a measure of how much you're losing of electrons in the surface and bulk. So an example for an established architecture like gallium arsenide is that we grow it in a chamber, a reaction chamber, and then we have to pick a temperature in which a chemical reaction has to occur. This is usually very time consuming because the throughput of these chambers is low, but also that you need a bunch of different measurements to actually get pinpoint within this stack what's the main part of the cell that is being affected by certain condition. So what something we have done here is this Bayesian hierarchical model. It goes from process condition to material descriptors. We could have some physics-based parameterization or replace it by a non-parametric model like a Gaussian process or a Bayesian neural net. And then we can go from material descriptors to the model output to the current. Usually by what we call a forward device model, which is a model that based on material descriptors solves a system of PDE equations, partial differential equations. But the challenge here is that they're usually pretty slow, hard to escalate to different samples. So we'll get back to this later. But one thing we can actually do here is to, once we have this hierarchical model or any sort of graphical model, we can perform things like Bayesian inference to actually identify that latency ABC here. So we might not need, if we have a good parameterization here, we might not need even that much data. So now going back to the device model, what we could do is replace it by a neural network. And we start by generating 50,000 semi-random combinations of material parameters. We apply it in our solver, well calibrated, and then we compute the current voltage characteristics for different illuminations for these 50,000 combinations. We use this data to train a neural network architecture, which is this convolutional architecture, 1D convolutional architecture. And essentially what we could do is We could train first a decoder and encoder, a noise encoder architecture to deal with the experimental noise that we have doing measurement, and it's also the difference between the physical model and the real data we have. And we can just apply like a regression model to relay material descriptors to different voltage characteristics. So this model is, or this surrogate model is actually pretty useful because it gives us denoising capabilities and also is 100 times faster than the usual PD model. Then it can allow us to do like MCMC, for instance, to infer the latent parameters. So this is some of the results that we got from the inference, in which we have 5 device parameters as a function of temperature. This is a lot of detail that usually have taken by traditional methods a lot of different runs of the MOCVD reactor. What we see is that these parameters are optimized at different points in the at different temperatures, and based on that we can construct an optimal growth profile, which is shown here. And what essentially we did was using this optimal growth profile here referred as BaseNet. What we did was synthesize more samples, and then we got this bumping efficiency, which is around 1%, which is significant for a single cycle of learning using maybe 20, 30 samples at constant temperature. And we estimate this like 20 times faster than the traditional method of characterizing the devices. And the closing idea is that usually in the lab, we optimize for record efficiencies, which is what give researchers, for example, a Nature paper. But if we want to scale quickly, probably we should start looking to the whole efficiency distribution of a solar cell and see how can we optimize it according to more manufacturing relevant conditions like the manufacturing yield or the variability. So what we see here is what we could do is, if we have an efficiency distribution, we could like convolute the value of efficiency function that give us considers things like the marginal value of efficiency, so how much dollars we get from this additional efficiency, or considers what's the minimum market competitive efficiency. That would give us a more effective figure of merit to optimize for. And this is an example for optimization of perovskites using 2 variables, solvent ratio and temperature. And here we can see that on top, we see the different conditions, for example, maximum efficiency, minimum variability, etc., are optimized at different conditions. If we apply our method, we can actually lump all these conditions into a simple metric that is important for like manufacturing relevant optimization. So we envision this could be useful for when you start moving cells that are optimizing a lot to actually industrial production. And another interesting thing that you could do is that you can apply the same inference model to extract the material parameters at each one of the different optima. And what this gives you is like, if you have 5 material parameters that correspond to different parts of the cell, I will give you a roadmap of what you have to prioritize according to what you are optimizing for. So for example, if you're optimizing for maximum efficiency, you'll optimize for this combination of parameters, compared if you're optimizing for more manufacturing relevant metric, which we call revenue, you'll have a different combination. And in conclusion, just to close the talk, is that machine learning is useful for accelerating development of solar cells and also in general in material science. And it's important to combine it with like physical knowledge or physical models, which give us both interpretability, but also to reduce the number of samples we need. So I would like to thank my sponsors here, and I invite you to take a look at the research groups that actually lead these projects. Thank you.
Thank you so much, Felipe. Yeah, so if anybody in the audience has questions for Felipe, please feel free to drop them in the chat. So maybe starting off with a question. So Felipe, you got in the end of your talk, you sort of mentioned this idea of somehow integrating physical models into into the machine learning models. And this is in fact, just to tie it all together, a topic that one of the speakers earlier touched upon today. So the idea of integrating physical models into machine learning. So maybe broadening that question, or broadening the consideration, I want to open it up to all three of you. What is your view on the role that machine learning and data versus traditional physics and science play in the scientific areas in which you work? And then what is the best way to combine these two worlds? Whereas what are the kind of different aspects of value that the physical models versus the machine learning models are providing? Hopefully that question made sense, but basically about the relationship between machine learning methods and physical models in the particular scientific domain that you study.
I can
Go for
start
it.
off quickly. Yeah, so I expect most of us to probably say similar things about this, but I would say one really key aspect is that it's not just plug and play. So one thing that I've noticed is that the key part is like understanding which models are out there and which models may fit your kind of data well is one aspect to it, but actually having some kind of physical intuition for what is really happening, what the data is doing, how you might architect a model to extract the kind of information you're trying to learn, especially with limited data, which is almost always the case. We just don't have unlimited data that's labeled. That's really where the hard part lies. So it does still feel to some degree like there's, human expertise is flowing in, doing a lot of the heavy lifting. Even though with these kind of deep learning models and with sufficient data, you can outsource more and more of the sort of feature extraction and those kind of things to deep learning models. There's still some human intuition that you need. So you need the people who end up doing the best work in these kind of projects, I find, are people who really understand intuitively, kind of physically what's happening with the data, but then also have been exposed to enough deep learning, machine learning. So having only one of those skills usually isn't enough to do it justice. And I think, as you say, Priya, there's definitely, it's not a replacement of sort of more traditional first principle based methods. It's really an augmentation that needs to very actively engage these first principles based methods. In my example, that would be, I talked about reinforcement learning for fusion, but we can't run a reactor and let it disrupt thousands of times to teach an algorithm how to avoid disruptions. Like, we just can't do that. So we need good simulators and we need to interface with those. So that's absolutely key, as you mentioned as well.
Awesome, thanks, Julian. Felipe or Yunwei, do you want to weigh in on that?
So I also have similar views as Julian. I think he made very good points. One important thing is that we also have limited data in, like, scientific experiments are usually pretty data limited, even in the best case scenario. And also there's a lot of noise coming from a lot of different sources, right? So like controlling noise in like real experiments is actually pretty complex. That's the reason we need like scientific insights. And sometimes even scientific insights are more valuable than the actual predictive power I have found. The other point is that if you see, I think a lot of like great progress in machine learning has been done in data sets that are like very easy to, in a way, understand. For example, images or a language that you could actually debug easily. But sometimes what you find in like physical sciences that you build a machine learning model, you make predictions, but they are like very difficult to interpret. For instance, if you are generating like materials or like molecules for drug discovery, what you find sometimes is that you have these amazing molecules that are very promising, but you don't know how to make them. So I think it's some sort of a two-way street, like the machine learning informs the experiments should inform machine learning. That's kind of my view.
Very cool. Yunwei, do you have anything to add on that?
Not really. Okay.
And I guess I'll ask one last question adapted from an audience question before we move on to the next session. So one of the audience members asked a question to Yunwei specifically about dealing with uncertainty, for example, in inputs and in the models and in future conditions. And Yunwei, you mentioned that you capture this through sort of the width of the credible intervals in your Bayesian model. So I wanted to kind of open this up more generally to all the speakers. In general, how do you kind of envision dealing with uncertainties relevant to your scientific domain in the various approaches that you construct? So for example, intervals is one approach, but are there sort of others that you would think the audience should consider in terms of incorporating this kind of uncertainty?
Bootstrap to compute confident interval.
Bootstrap, you can try Bootstrap.
Yeah, cool. Felipe or Julian, any other thoughts about that? So bootstrapping is one.
What I think is that, for example, these like structural Bayesian inference models are actually pretty useful, like graphical models. I have seen like approaches of using like deep learning to learn these like graphical models, for instance. I think those are pretty promising. And the other thing is like Bayesian neural nets, right? Like, could we like make progress in Bayesian neural nets that actually are robust to apply in real problems? I think that's a big thing that we should like as a community aim for. Yeah, I think just because you'll have like representation, like feature learning power, but also uncertainty. And for in our case, in experimental settings, I think that's super, like uncertainty is like critical, right? So I think that's a very, very good opportunity area.
Awesome. Okay, I guess with that, we will close out the session. Thank you so much to our speakers. That was a really great assortment of different, again, scientific applications of relevance to climate change that machine learning was plugging into. So thank you for that wonderful overview. I'm going to hand this over to Sharon Zhou in just a second to introduce our next session, which is a fireside chat on remote sensing and artificial intelligence. So everyone in the audience, if you could just give us 1 minute as we get set up, we'll start the session shortly. And again, thank you so much, Yunwei, Felipe, and Julian for sharing your insights here.
Thanks, Priya.
Thank you.